Hey everybody, I thought we would take what we learned yesterday about inclined planes and apply it to some quantitative problem solving. So let's take a look at this problem that's given. We have a block that's sliding down a ramp, so I'm just going to sketch what we have going on here. So we've got just sketching the ground there, and then it says we have a ramp. And the angle that the ramp makes with the horizontal is 35 degrees. So I'm just going to sketch that in. And then it says we have this block on the ramp. And the block is accelerating down the ramp. So we've got an acceleration here of 0.3 meters per second squared. Okay, what we know is that we know the mass of this box is 14 kilograms, and again that acceleration is known and the angle of the incline. Okay, so what I want to do now is I want to assign a coordinate grid, like some kind of x and y axis, and start sketching in my force diagram. Alright, well, to start with this force diagram here, I know that I can sketch in force of Earth on the object here. That'll be mg. And because the mass is known here, I know that this will be 140 newtons. I know that the normal force will be perpendicular to where the two surfaces meet, so the normal force will be here. And any frictional force will be opposite of the motion of the object, the velocity. It says the box is sliding down, so I know that I also have a velocity down the ramp. So that means friction will be in the opposite direction here. It'll be some type of kinetic friction force. I'm not really sure how much it is. Okay, so I'm going to sketch in my x and y axes. I'm going to have my y-axis align with my normal force and my x-axis here align with my frictional force. The next thing I'd like to do is I'm just going to re-sketch those axes here. So here's my y and here's my x. And I'm just going to draw in the forces that I have that align with those axes. So here's my normal force, here's my frictional force. And my job now is to resolve mg. So notice the angle of the incline is given here, and I know that I can take the angle of the incline and find the y component of mg. The y component of mg is going to be mg times the cosine of the angle of the incline. So let's say theta is the angle of the incline. Because I can imagine here this block sliding down the inclined plane, I know that acceleration in the y direction is 0 meters per second squared. This box will not be accelerating along this y-axis, so therefore the net force in the y direction will be 0 newtons. I know that mg cosine theta then must equal the normal force. Now I also know that I have this acceleration vector that is going down the ramp. So I also know that I will have a net force in that same direction. So I'll have a net force in the x direction. So whatever I make my x component of mg, it has to be longer than that frictional force in order to produce this net force in the x direction. And this will be mg sine of theta. Okay. So I know that acceleration in the x is some number, right? So in my x direction, I've got some different things going on. I've got an acceleration this time. So I also have an F net. And the F net in the x direction can be found by doing mass times acceleration in the x direction. And I do have both of those numbers, so I'm going to go ahead and handle that. I know that the mass is 14 and that the acceleration is 0.3 meters per second squared, which gives me a net force in the x direction of 14 times 0.3. Grabbing my calculator here, it gives me 4.2 newtons. Okay. Let's find our x and y components of mg so that we can finish our problem. Okay, so our mg cosine theta is just 140 newtons times the cosine of 35 degrees, and that gives us 115 newtons. When I look over at my force diagram, I have this going in the downward direction, so I'm going to have my downward direction be negative, so this should be a negative 115 newtons. And then to get that x component of mg, it's mg sine of theta, where theta is the angle of the incline, and that gives you 140 newtons times the sine of 35 degrees, which gives you 80 newtons. And then looking at the picture here, I'm going to have the right side of my axis be positive, so I'll just leave this as 80 newtons. Okay, now going back up here to my second law statements, I'm going to take a look at what's going on in the y direction. We know that the F net in the y is 0 newtons, and this means that 0 newtons is equal to mg cosine theta plus our normal force. So this means that 0 newtons is equal to negative 115 newtons plus F normal. So that means that F normal is 115 newtons. Okay, great. So now we know this guy is 115 newtons. We also found that this one is 115 newtons. We also know that mg sine theta is 80 newtons, so I'll just add that in here. And now our only unknown is the force of friction. Okay. So our net force has to be 4.2 newtons in the x direction we found. So let's set up a net force in the x statement. Our net force in the x direction would be equal to force of friction plus mg sine theta. Our net force is known. It's going to be 4.2 newtons. Our friction is an unknown, and our mg sine theta is 80 newtons. So if I subtract 80 newtons from both sides, I can get our frictional force. And that'll be negative 75.8. for our frictional force. So we found our frictional force, we found our normal force. We could also find the coefficient of friction, so we could also find mu. The coefficient of friction would be equal to, well, let me just use the math model for friction. Friction is equal to the normal force times mu, and if our frictional force is 75.8, and our normal force is 115 newtons, what is our coefficient? Well, I'm going to divide both sides by the normal force. And if I do that, I end up with 75.8 divided by 115, which gives you about 0.66 for your coefficient of friction. Well, I hope that you found this example for problem solving on an inclined plane useful. There are videos that follow with more examples for inclined planes, so please feel free to check those out, and I hope you're having a great day.